Okay, so this is our introductory lesson to chapter 3 or module 3. This is going to be kind of our proofs chapter. We're going to learn kind of the ins and outs of proofs, but before we get there, we have to learn about some terms and some kind of useful things to us before we dive in. So today is going to be kind of one of those lessons where it's more about understanding the concept of what's going on, more so than it is we're learning a new math trick or tool or something like that. So first things first, it's a good thing to always pause these videos and try the warm-up problems. So when we go to look at this, just to kind of start us off in the right direction, what they're asking you to do here is to analyze these patterns that are happening and then kind of make a general statement based on what's going on. So in this warm-up, we have kind of again, it's squaring some odd numbers, and then it's asking us, well, okay, what generalization can you make about the square of an odd number? So in number 1, for instance, the square of all these odd numbers is yet another odd number. So take a second to pause and try these, and then I'll slide down to the answers given once you've had an opportunity to try. So hopefully you took a second and tried those, but you can see the answers given there. Again, a lot of these are math things that we've known before, but we're just reiterating that that's the way that it will work all the time. Okay, so kind of along that line, what we're going to learn about today is conjectures and counterexamples, and we're going to learn about what inductive reasoning is. So kind of make sure that that's your main pull away from this lesson, is that I should know what a conjecture is, what inductive reasoning is, and what a counterexample is. So to start this off with, inductive reasoning, what you really need to do to highlight this in your notes is understand at its very core that it's a reasoning using patterns. Okay, so inductive reasoning uses patterns. You've done this since early elementary school. You've used and followed patterns to list the next term. You've made generalizations in a lot of classes based on observed patterns. Okay, and then the next term down here at the bottom is a conjecture. Now, this is a new term too, where essentially it's a term that we've used or we kind of know. Again, if you look at this, it says an educated guess based on known information and specific examples. So again, it's kind of like a hypothesis, but it's in math. Okay, so a conjecture is essentially, it's using these patterns to make a guess. Okay, so you're using inductive reasoning to make an educated guess. That's a conjecture. Okay, so as we move forward, in example 1 here, you can see it wants us to write a conjecture based on the pattern of the sequence and then use your conjecture to find the next term. So our answer isn't simply the next term or the next 3 terms in the pattern, but we want to write a statement based on what we see. So you have appointment times here, and if we look, each appointment time is 45 minutes later than the next. So that can be our conjecture. Appointments happen every 45 minutes. Okay, and again, once we have that pattern kind of down, now we can make our statement, or now that we've made our statement, now we can say our next appointment time should be at 11:30 a.m. Okay, so again, take a second to try this. Make sure you try and fill in the blank. But once you have an opportunity, you can go ahead and hit resume. So again, hopefully you took that opportunity. It says the next number in the sequence is double the preceding number, or you could have put 2 times, whatever you want. The next number in the sequence is going to be 8. Okay, so again, this is a conjecture based on a pattern observed. Okay, so here's kind of where we're going to end up having some of our questions more lean on to. Rather than focus on geometry stuff all the time, because our pool of knowledge isn't that deep yet, we're going to refer to a lot of things that we understand already about math. A couple of things to kind of make a note of. It assumes that you understand what the natural numbers are, the real numbers, the integers, and the whole numbers. So make sure you brush up on that. If you need to, ask questions in class, and I'd be happy to kind of go over that with you. But here it wants us to make a conjecture. And first, before we can make a conjecture, I would say come up with at least 3 examples of your own before you make a conjecture. 1 and 2 really just don't seem sufficient to make a general broad statement about a case that would happen all the time. So as we look at this, 1 squared plus 2 squared is 5. 2 squared is 4. 3 squared is 9. We add those up, that's 13. 6 squared is 36 plus 7 squared is 49. We add those together, we get 85. 10 squared is 100. 11 squared is 121. We add those together and we get 221. So it says, notice that all of those are odd numbers. So the sum of the squares of 2 consecutive natural numbers is always going to be an odd number. Okay, so again, we listed off some of these. This is just the numbers that the book picked. You could have done any 2 consecutive natural numbers. Again, natural numbers are counting numbers, so you could have just as easily done 100 squared plus 101 squared, and you should have still gotten the same result. So now again, take a second to pause. Try and do, again, at least 3 examples to make your generalization. So as we look at this one here, it says the sum of 2 odd numbers. Now, I've had a lot of kids do a repeat. So 3 plus 3, we can do that, is 6. I've had kids do consecutive odd numbers. So let's say we do like 3 plus 5. Okay, we get 8. And again, kind of a good thing to do is let's do some that aren't in a row. So like 1 plus 15, we get 16. So listing these off, and again, hopefully you did some as well, but listing these off, we should be able to make a general statement that the sum of 2 odd numbers will always be an even number. Okay, kind of along the lines of using this tool with geometric things. And again, I don't want to dive too deeply into it, especially in things that we haven't discussed in class together yet. But they have a generalization about isosceles trapezoids. Now, again, we haven't even talked about isosceles trapezoids, but they list them off. Again, isosceles means that you have 2 congruent sides, and obviously it's not a triangle, it's a trapezoid. But if you look at the dotted lines in these 3 images, they look to be the same. So the diagonals of an isosceles trapezoid look to be congruent. The reason I have this term written over here is because if we see more of stuff like this in the practice set, GeoGebra is a really useful site where you can actually create some shapes and manipulate them to kind of help you make some of these generalized statements. But you can see here the conjecture made is that the segments joining the opposite vertices or the diagonals of an isosceles trapezoid are going to be congruent. Okay. Now, again, this is one we want to go over in class, and I've covered this, but because this is midpoints and we've actually learned about midpoints, it'd be nice if we could at least illustrate this. So if you can, try to illustrate this image before you go ahead and go on, and see if you can't make a generalization. Okay, if you need the assistance, I'm going to go ahead and start. So what we're going to start with is segment AB. Because in our first sentence, after it asks us to make a generalization, is it says that C is the midpoint of AB. Now recall, the second I see the word midpoint, I should be able to make a congruent statement every single time. So I have AC is congruent to CB. The next thing it tells me is that D is the midpoint of AC. So now, not only do I have a midpoint in the whole segment, I have a midpoint on half of the segment as well. So you can see here that point D creates another equivalence statement. AD should be congruent to DC. Now, if I just look at this image with respect to the whole thing, we should be able to make an observation about the segment length of AD with respect to the segment length AB. And that is, it should be a quarter of the length of AB because it's a half cut in half. Okay, again, just briefly touching on this one, if we look at the pattern in gas prices, from here to here, it's going up. And then from here, clear to here, it's going down. Okay, and then it asks us what generalization could we probably make about the cost of gas in 2019. Again, the price of gas will probably increase because it's going to go up and then down and then probably up, and it'll keep doing that for a while, I'm guessing. Okay, this one again is another good one. Again, pause, read through it. It's really not as complicated as it seems. Again, pay attention to your unit of measurement here. But as you pause it, just look at your units of change along the left and the right and see if you can't figure that out. Okay, so again, as we look at it, it's going up by 3. So at 103, the pattern is we can be exposed to it for 1/8 of an hour. That means at 106, we can be exposed to it for a 1/16 of an hour. So if I go over here and I try and convert this into minutes, I'm just going to take 60, divide it by 16. And again, whatever decimal that is, that's how many minutes it is that you can be exposed without damaging your hearing at that decibel. Okay, the next thing is counterexamples. And again, counterexamples are a really useful tool for us because they're not as broad as conjectures. Conjectures kind of get challenging at times because we have to come up with a bunch of examples to try and make a statement that we can assume to be true. It might not always be that way. What's really nice about counterexamples is that you only have to come up with one specific example that contradicts your conjecture, and that means it's not true all the time. Okay, so again, conjectures, you're trying to say something is true all the time. Counterexample is you can say, no, that's not the case because of this one specific case. Okay, so the example that I like to give is that, if it's 40 degrees outside, every kid that comes to school today is going to be wearing long pants. And then all you have to do is name a single student that comes to school in shorts, and that's your counterexample. You don't have to come up with all of them, just the one. Okay, so as we look at this one, again, if you think about it, it says if n is a real number, again, the reals are the positive and the negative counting numbers, then negative n is a negative number. Well, that's not always true because if I let n equal a negative number, the opposite of a negative is going to be a positive number. Okay, also, a lot of times with these counterexamples, 1 and 0 is super helpful. So if I think about plugging in the number 0, 0 is a real number also. If I plug it in, -0 is not a thing. So it's also not negative, it's just 0 still. Okay, so keep in mind negatives, 0, sometimes fractions help us in counterexamples. Another good counterexample is this one right here at the bottom. It says if A, B, C, and D, B, E are congruent, then A, B, C, and D, B, E have to be vertical. Now again, with them sharing this vertice in the middle, we've seen lots of cases where this is true, where A, B, C, so A, B, C is congruent to D, B, E. Okay, and again, that's because they're vertical, but they're asking you to come up with a case where that's not true. Again, all we have to do really to make that the case is just slightly tilt this image so we can take this angle and kind of tilt it away so that these are not collinear. So as you can see here, they take an image and they just kind of twist it a little bit. You can see the congruent markings. They share vertice, but those are not vertical angles. So again, when points A, B, and D are non-collinear and points E, B, and C are non-collinear, the conjecture is false. Okay, so again, in the figure, ABC is congruent to DBE, and ABC and DBE are not vertical angles. That's our counterexample. Again, counterexamples can absolutely be an illustration. You don't have to have some long-winded thing. You can just give a specific case where it's not true. Okay, so on this skill check, plug in these numbers and see which one of them would work for a counterexample. In other words, would disprove this statement right here. And then illustrate on part B something that would work to make that not true. Okay, so again, pause and try it. Now that you've had an opportunity, hopefully you've paused it and tried it. But if I plug in -3, for instance, at the bottom, I have 1/3 and it's negative. Let's make that a better color to see. I have -1/3 is less than -3. Well, hopefully we all know on a number line that that's not the case. So A would work as a counterexample. Okay, if we look at B, again, this looks kind of silly, but we don't divide by fractions. We multiply by the reciprocal. Well, that means that this says 4 is less than 1/4. So odds are if I pick any improper fraction that's positive, it's also going to work as a counterexample. Okay, again, another one here. We have 1. this one's going to work as well, because again, 1 over 1 is not less than 1, it's equal to 1. And that's not what it's asking. It's asking for less than example. So this one is also a counterexample. Now, obviously, if we plug in 5, 1/5 is less than 5, 1/100th is less than 100. So positive numbers are going to satisfy that conjecture. We want ones that don't, okay? And the second one, a lot of students really hesitate to try this, but it's actually very simple. So I'm going to illustrate a midpoint, okay? And it says every time a segment gets cut by another line, it's going to be a perpendicular line that creates the midpoint. All you have to do, draw a line that's not perpendicular. Done. Okay, there's your counterexample. Okay, so again, take a moment, pause, try and give counterexamples for each of these. Once you've paused, go ahead and unpause the video and check and see if you got them right. So there you have it. Again, make sure you ask questions on the practice set. If you have any, please make sure you understand those big terms today. Again, conjecture, inductive reasoning, and counterexamples.